Hey, welcome back, everybody. Here's the second video for accumulation functions. I hope you found the first one helpful. Then my goal for this video is to definitely make it a little bit shorter. We can try and get through the content a little bit quicker for you. If you haven't done so already, please check out the review of the last free response question that I assigned for homework. I put a video up on my Malvern as well. And so if you have done that, I hope that that was helpful. And continue to let me know if you have any questions, throw them on the Google Doc or send me an email so I know what's going on. Okay. And also very quickly, just a shout out for me to the whole class. I would really like everyone to at least check in during class time on the Google Doc. So even if that's just a, hey, I watched the video, or hey, I'm working through the video, did fine on the homework, whatever it might be, just a quick check-in just to see how you're doing. And so I can hear from you and just kind of make sure that you're on the right track. All right. So please continue to do that. Check in during class time on the Google Doc, even if it's just for a quick see how you're doing. All right. I'll also be posting updates there. So you need to kind of continuously check that Google Doc. I'll try and do that as well in my Malvern, but there are some things on there that you definitely want to read. Okay. All right. Let's get into it. So the second video is more about an application. Okay, so the first video was all about analyzing a graph. This is more about sort of real world based examples. I'm using quote unquote real world because some of the examples may seem a little bit silly, but they really do kind of get the point across as to what these accumulation functions can do for us and how we can use them. So what we're going to have to do is definitely use or possibly even create accumulation functions based off of the scenario that we're given. We're still going to have to evaluate derivatives, evaluate accumulation functions. We're going to have to derive accumulation functions, and then we're going to have to still talk about, what do they mean? What do they give us? And what type of information can we pull through them? So let's take a look. Here's just some reminders. Average rate of change is something that comes up frequently in these types of problems. I'm going to base this whole section off of free response questions that the AP has released in the past. They're really good models as to what types of problems you'll have to do. And again, they're good examples of how this stuff can be used. Excuse me. So average rate of change, something that's going to pop up, right? Y2 minus y1 over x2 minus x1. We've talked about that a lot. Just throwing it out there. Quick note here, a positive rate of change. So a positive derivative means a quantity is increasing. A negative rate of change or a derivative means a quantity is decreasing. We're talking about real application here, right? So these derivative functions, these derivative models, rate of change models are going to actually be explaining something that's happening in the real world. Okay, so something's going to be increasing or decreasing in some way, shape, or form. The accumulation is the integral of the rate of change function. So this is pretty much everything that we've been talking about. This is what it's all been leading towards with integration. If I take the integral of some rate of change function and it's positive, there was some type of accumulation or increase in that quantity. And then oppositely, right, if the integral is negative, some type of dissipation or decrease in the quantity. So again, think about snow is falling. I know the rate at which snow is falling. If I take the integral of that rate of change function over a certain period of time, I would know how much snow has fallen on the ground. It's that exact idea. So some pieces to look out for. Units are a big part of any real world type application problem. So definitely take note of those right off the bat. This can get a little bit strange because we're typically starting with a rate of change function in these problems, and then we might be asked to take the derivative of that rate of change function, which is a second derivative. And so interpreting those units is a little bit different. It can look a little bit strange. So we'll actually talk about that a little bit today. And then here are just some examples of rates of change units, right? So anything that has an amount followed by a unit of time, right? A unit of time. So pounds per hour, beat per hour. And then this last one down here is what I was talking about in terms of discussing units of a derivative, like a second derivative function of some sort. So liters per hour, which is also liters per hour squared. Most commonly, you've probably seen that with meters per second squared for acceleration. That same idea. Initial values are really big in this section. Almost every single problem starts with them in some way, shape, or form, right? And so typically at time t equals 0 or at some time during the day, you have to ask yourself, is there already a certain amount accumulated or in place? What did the problem give me? Is there some initial value? And the most important piece of the problem that comes into play is if we have to find a total amount of whatever has accumulated or dissipated or whatever it might be after a period of time, we're always going to have to add that initial value to the accumulation function in order to get the total amount over a certain period of time. Specifically, if we start at that time t equals 0. And then this last bullet, this is specific to the types of questions that we'll see regarding finding a total amount after a period of time. So initial value is part of that, but this is also a big part. If something is like dissipating, which means it's being removed, maybe it's like melting or something, and it's lessening in some way, whatever it might be. People leaving a concert, is a dissipation of people from that concert. That could be happening at the same time that an accumulation is happening, right? So think about, we've done water into a bucket, right? So I'm pouring water into a bucket, but then I poke a hole in the bottom of the bucket. I have an accumulation of water as it's coming in, but I'm also dissipating. The water is emptying through the bottom. So that's happening at the same time. I could have a rate of change of both of those things, right? So the rate at which the water is accumulating inside and the rate at which the water is leaving, both of which could have their own quote unquote accumulation functions. But we're going to be able to create one full accumulation function that tells us the whole story. And whatever is dissipating or being removed or whatever it might be at that time, we're just going to subtract that rate of change from the rate at which something is accumulating or filling or anything of that sort. Okay. And again, we'll talk about that a little bit. Just some things to look out for that are definitely going to happen. The second fundamental theorem is going to come into play here. Whenever we are creating or dealing with an accumulation function, and again, accumulation function is an integral with an upper bound that is a variable, usually x, we're almost always going to have to take the derivative of that at some point in time. And typically how we're asked to do that is to find a minimum or a maximum amount. And so I know the amount is found by finding the accumulation function, so creating that accumulation function. And then minimums or maximums are found by taking the derivative of that function and setting that derivative equal to 0. So that will come into play throughout this last part of this unit. We'll talk a little bit more about that. I'm happy to answer questions as they come up. All right, let's jump right into the problem. So this is the problem I want to base all of today's instruction off of, and then you'll have something really similar to this type of problem to try on your own. So let's look at the scenario and just go through the intro here a little bit before we get into the problem so we can pick out all the pieces we need. So I want you to start visualizing this stuff happening, right? Because you've actually started visualizing these scenarios. I really do think it makes these problems a little bit easier to get through. So this one, again, may be a little bit silly, but I actually think it really does a nice job of getting the idea behind accumulation functions and rate of changes better into your mind, better idea of like, what is this math actually telling me and how can I use it? So this scenario is where you walk into a grocery store, right? When it opens. And as soon as you walk into the grocery store, you see a banana stand or a banana display table. And right at the beginning of the day at t equals 0, that banana stand already has 50 pounds of bananas on it. Okay. Throughout the day, obviously customers are going up and they're taking bananas off of the stand. Right. And in particular, for this model and for this day at this grocery store, from the time it was open, t equals 0, to 12 hours after, right? So from 0 to 12, the rate at which bananas are being taken off of that display table is modeled by this function, right? So this function does not give me the amount of bananas that are taken away. It's the rate at which they are being taken away. Okay, so this is a rate of change function, or a derivative, if you will, already. Okay, something important to note here is that this is, if you want to say it, like a dissipation, right? I'm losing bananas from the stand, so I'm lessening the amount or I'm decreasing the amount of bananas. So this is already a dissipation, not necessarily. I'm not accumulating bananas, right? They're getting taken away. A couple of things I want to point out here. The function f is measured in pounds per hour. Again, reiterating the fact that this is a rate of change function, not an amount function. That's not the amount of bananas. And then t is the number of hours after the store is open. Okay, so at t equals 0, the store is open. Any hour after that is just time moving forward. Okay, so that's what's happening with things leaving the bananas display table. Obviously, though, after a while, store employees might say, man, that display table is really getting low on bananas. We need to start restocking it, right? So this happens exactly 3 hours after the store is open. So for the first 3 hours, bananas are on the table. People are going in, they're taking bananas off, and nothing's really done about it. But at 3 hours, the store says, hey, we need to get more bananas on that display table in order for, so it doesn't run out of bananas completely. And so we have a rate of change function, G of T, that shows me exactly how fast or the rate at which the employees are putting bananas back onto the table. So this is sort of a true accumulation function, right? Or it leads to a true accumulation function. It is the rate at which bananas are being put back onto the display table. It is also measured in pounds per hour, and T is still the number of hours after the store is open. So those match, which is good. We don't have to do anything with units and trying to match them up in any way, shape, or form. All right, so we're already there. Okay, so we've got the scenario in our head. Hopefully you feel pretty good about that. If you don't, pause the video, read over the question again, and come back. Okay. At this point, this is a calculator active question, and all of these types of questions, especially with weird functions like this, are going to be calculator active. So I encourage you to get out your calculator and put f of t into y1 and g of t into y2, or vice versa. It doesn't matter. Just make sure that you know which one is which. All right. So again, pause the video at this time if you don't have your calculator, just to kind of walk through it with me and go on from there. Okay, so part A, let's jump into the actual problems here. This is a really typical first question for this type of problem. I want to know how many pounds of bananas are removed from the display table during the first 2 hours. Basically, what I'm just trying to say is, well, okay, you've given me a derivative, which tells me how fast something is happening. I want to know the amount at which, or the amount that either accumulated or dissipated over that time. And so the main thing to point out here is that we're talking about the bananas being removed. There's nothing about the bananas being put back. So as soon as I see that, I know that I'm only talking about f of t up here. Okay, so I'm solely dealing with f of t, which might be y1, right, in your calculators at the moment. And then the second piece is that I'm only talking about the first 2 hours. So I know the store opens at t equals 0. After the first 2 hours is t equals 2. And so if I'm trying to figure out the accumulation of the total number of bananas that have been removed, I'm going to take this rate of change function and put it into an integral, right? And so specifically, this is a definite integral from the time it was open, t equals 0 to t equals 2. And that's actually going to give me my answer. So I'm going to scroll down here and look at the slide for the answers. And so this first part A, relatively straightforward computation. I'm going to take 0 to 2 of f of t, which would be y sub 1 in your calculator, and get an answer. Okay. And so typically answers on the AP exam extend out to 3 decimal points. That's why you see that. And then I just have my unit, which is pounds, right? No longer pounds per hour, because this is the exact amount that was removed during the display table for the first 2 hours. Okay. We have to explain all parts here, because your answer is really dependent upon, well, what does this integral mean and how can you say it in words? All right. So this integral that you have up here is actually being described perfectly in words with this explanation. And notice the point amounts here that you would get for that answer. Okay, part B. Find f prime of 7 and using correct units explain the meaning of f prime of 7, specifically in the context of this problem. Very important piece right there, which we'll get to. Important to note that I'm taking the derivative of f. We'd already said that f is technically a derivative already. It is a rate of change. So really you can think of this as finding the second derivative of whatever the function is that tells me the amount of bananas that have been removed. This is going to come into play specifically with using correct units, which we talked about earlier in the video. Okay, so for computation purposes, this is actually really easy because it just says find f prime of 7. Well, that's as easy as I know that this is the function they're talking about. I need to take the first derivative of f and plug in 7. Okay, so in your calculators, this is really easy. We don't even need to show what the derivative is if it's a calculator active problem. All I need to do is go into my calculator, math 8, y sub 1 evaluated at 7 and what that number might be. And so let's jump to the answer and talk about the explanation a little bit. So if you did that on your calculator Again, pause if you haven't, just to make sure that you're doing that correctly and you got this number. You should get f prime of 7 equals negative 8.120, or this guy, which both would have been an acceptable answer. So hopefully you got this answer. And if you did, the explanation is probably more important than the actual value itself. And so what this says is we have to explain every part, specifically starting with, well, what does the 7 mean? Why did you put 7 in here? What does that tell us? Well, the 7 is the time at which we're talking about. And so in this case, at t equals 7, that's 7 hours after the store has been open. So that's an important piece. We have to note that this is the time of day we're talking about. The rate at which bananas are being removed. So I'm again using the removed function, is decreasing by 8.12. The most common mistake with these types of questions, I can't stress this enough, is if we get a negative derivative or negative value from your derivative, that means that the amount is decreasing by the positive number that you see, right? The absolute value of this derivative that you found, okay? We do not want to write it's decreasing by negative 8.12 because that's a double negative, which actually means it's increasing, which is not true, okay? We're taking bananas off. It's decreasing by 8.12. All right. And then finally, your units, which are very important, pounds per hour, right? So this is your second derivative. It's pounds per hour squared or pounds per hour. Hopefully that makes sense as to why you did that. If not, let me know. Okay, part C. Is the number of pounds of bananas on the display table increasing or decreasing at time t equals 5? Give a reason. So we are specifically talking about how fast things are being taken off versus how fast things are being restocked. Okay, it's at t equals 5, so the restocking has already happened. If I can put more bananas, if I can restock bananas faster than customers are taking off the bananas, then my number of bananas is increasing at that time. We've actually already done problems similar to this in the past, so I'm hoping this is a little bit familiar to you, okay? So I really just want to compare the value of f of t and g of t at t equals 5. Whichever one is greater is going to win. So if g of 5 is greater than f of 5, then more bananas are being put on than being taken off. So the number of bananas is increasing. Vice versa if f of 5 is greater than g of 5. And you can write this in a couple of different ways. So I'm going to get to the answers here in just a second. But again, if you're using your calculator, pause and try and figure out, well, what is f of 5 and what is g of 5? In your calculators, that might be y1 of 5 or g of 5. You could also go into your table and put that in there, okay? So you can put f of 5 and g of 5, y1 of 5, y2 of 5, see what those numbers are, and just compare the two. If you look at the actual answers itself, it does a subtraction here, right? So if I take g of 5 and subtract it from f of 5, if the answer is negative, that means f of 5 was bigger, which means that it is, in fact, the number of bananas is actually decreasing because customers are taking bananas off faster than they're putting them on. And so that is the case here. All right. Again, if you didn't get this in your calculator, please try it again and go back and see what you might have done wrong. If you did get it, great. It's perfect. Okay. And here's your reasoning. All right. And so anything of this sort would really work. I think that that's fairly straightforward. And again, I think we've worked with that in the past. Okay, last part of the problem, and then that's really it for me. So this is the heart of the problem, I think. This is the true accumulation part of the problem. How many pounds of bananas are on the display table at time t equals 8? So think about this. It's not talking specifically about how many pounds are being taken off, how many pounds are being restocked. It's about the whole scenario. So everything that's happening sort of all at once. You have to account for both f of t and g of t. And so since we're talking about, I want to know the exact number of pounds, it's not a rate of change, I know I'm going to have to use an integral because I want to accumulate the total amount of bananas that have been restocked, and then I want to subtract the total number of bananas that have been taken away, okay, through that time. And so I'm actually going to jump to the answers here because I want you to see the setup, and then it also leads to the answer itself, and we can talk about the setup of the problem. So part D. First thing, very important. All right, we talked about initial values. There are 50 bananas on the display table at the beginning of the day. I have to start with that number, okay, because everything is based off of that. From there, I'm going to add the integral from 3 to 8 of g of t. I started restocking at t equals 3 hours, and I only want to go to 8 because that's what the problem is asking me for. So this is the total number of bananas that were put back onto the display table from 3 to 8, from t equals 3 to t equals 8. Okay, so this is sort of the total number of bananas that were on the table at any point in time throughout the day. But I want to know the total amount that is just they're sitting there after people are taking them away as well. And so I also have to subtract the accumulation or the integral from 0 to 8 of the rate at which bananas were being taken away. So bananas are starting or being taken away from the very start of the day. So I'm going to start this at 0 instead of 3 and go all the way to 8 again. And I'll subtract it because, again, that's the number of bananas that are taken away. And you should get this guy, right? And you can do this whole thing in your calculator. You do have to do 2 separate integrals here, right? Because there are 2 different time values. If we said, what's the total number of bananas from 3 to 8, just in general, I could start both these at 3 and then just do 1 integral. But since these are, I want to know from the start of the day, I have to do 2 different integrals, all right? Because g of t is not valid for 0 to 3. And there's your answer. Okay, so you get your answer in pounds of bananas, right? Not pounds per hour, not pounds per hour per hour. These are just the number of bananas on the display table at time t equals 8. All right, I hope this was helpful. I know this might be, you might have to get used to this a little bit, rewatch parts of the video, pause the video, let me know if you have any questions. I'm going to post this on my Malvern as well, but here is the problem that I want you to try. Again, it's very similar, but it has its own little pieces to it, its own unique parts that you have to work through. So please just kind of take your time, be patient with it. Let me know if you have questions. I'm happy to help. Basic idea. Sorry, that was a dog in the background. The basic idea here is that we have a drain pipe where water is flowing into it from one end, and then it's actually flowing out the other end of the drain pipe, but the drain pipe is partially blocked. All right. And so the rate at which water is leaving or dissipating from the drain pipe is modeled there, and the rate at which water is coming in or accumulating is modeled here. So very similar to bananas, just talking about water going into a pipe and leaving a pipe. And then here's your initial value, 30 cubic feet per your 30 cubic feet of water at time t equals 0. So that's your initial value. So roll through here. The ones I want you to be extra careful with are part C. This one's a little bit different. We're talking about trying to find the amount of water in the pipe being the minimum. So I want you to go back to the slide or the part of the video that talks about how do we find a minimum amount and what I have to do that. Just FYI, you're going to have to create an accumulation function, right? So what would the accumulation or the integral look like if you were trying to find the total amount of water from 0 to 8? Okay. Once you have that down, then you can take its derivative. All right. And think about, hey, there is an initial amount there still. Okay. And then part D is, I want you to work through that a little bit. Seems more confusing than it is. Okay. So give it a good shot. I'll be posting the answers and another review solution video of this as well to help you out. All right, guys, have a great day, and I'll talk to you soon.